Hello everyone. Today we are going to discuss some of the problems related to the designing of the train. That is, how many axles we require and how will be the acceleration and how will be the gradient and all. To calculate all those things, we are going to solve some of the problems, and it is related to the adhesive weight like that. So now we'll discuss one by one. So that is problem on design. First one, 400-ton train is to be hauled by a locomotive up a gradient of 2% with acceleration of 1 kilometer per hour per second. Coefficient of addition is 20%. Track resistance 40 Newton per ton and effective rotative mass is 10% of dead weight. Find the weight of the locomotive and number of axles if axle load is not increased beyond the 22 tons. So this is the problem we have. That means we have a train which is weighing 400 ton, and it is being hauled or it is being pulled by a locomotive up a gradient. That is, we have a gradient up gradient we have. Which is 2%, and the acceleration here will be 1 kilometer per hour per second, and the coefficient of addition is 20%, and the track resistance they have given it is 40 Newton per ton, and the effective rotative masses is 10% of the dead weight. So here we have to find out what is the weight of the locomotive and number of axles required if the axle load should not increase beyond the 22 ton. So this is the problem. First, let me list out the data. That is, gradient g is equals to 2% and alpha is equals to, that is acceleration alpha is equals to 1 kilometer per hour per second, and coefficient of addition, that is mu. Mu is actually 0.2, and train resistance they have given it is 40 Newton per ton, and the weight of the locomotive we have to find out. I'm denoting the weight of the locomotive as WL, and the dead weight of the train and locomotive we are going to take. Here we are not going to take only the dead weight of the train, because in the some of the earlier problem we were solving related to the specific energy consumption and all. There the weight of locomotive is not required, but in this something like designing problem we require the weight of the locomotive also. So hence the dead weight is nothing but what? It is actually the total sum of the weight of the train and also the weight of the locomotive. Hence it will be 400 plus WL tons. So this is the dead weight. And effective weight, how do we write this? Because by considering the effective rotating masses, we could write the effective weight as how? That is, WE will be equals to what? So WE will be equals to 1.1 times of the dead weight. Why it is 1.1 times? Because it is W plus W plus 0.1 W, which is nothing but what? 1.1 W, because effective mass will be always greater than the dead weight. Hence we have to write in this way. So dead weight here is 400 plus WL. Next, the tractive effort we need to calculate. So we know that the tractive effort formula is 277.8 WE alpha plus 98.1 WG plus WR. So this is the formula for tractive effort. And let us substitute the value. First, let me take the W common. So if I take W common, and WE by W will be usually 1.1. So that we will substitute here. Hence, we will get this equation. And we will upon solving we will get as 541.78 W Newton, because the dead weight, total dead weight I don't know, because the weight of the locomotive is unknown here. Hence let us retain the dead weight as W W only. So hence it is 541.78 W Newton. But actually we are going to convert the tractive effort also in terms of tons. Hence we need to convert the Newton to tons. So how do we do it? So we will be doing it by dividing 9.81 into 1000. So hence I could write it as, because here you can see the 1 1 kg force is nothing but 9.81 Newton. Okay, because if I take in terms of weight, weight is a vector quantity. Hence, I could write like this: 1 kg force is nothing but 9.81 Newton. So that we know. If I want to know what is 1 Newton, then I have to transfer 9.81 to the LHS side. Hence, it will become 1 kg force divided by 9.81. Let me convert kg to ton. So how do I do it? By dividing 1000. Hence, it will be converting into ton force divided by 9.81 into 100. So hence 1 Newton will be equals to ton force divided by 9.81 into 1000. Hence, I'll be dividing the answer by 9.81 into 1000 to convert Newton to ton force or to ton. So hence 541.78 W will be divided by 9.81 into 1000. Hence it will become tons. Hence, let us substitute the value of W, which is nothing but 400 plus WL. Let this be equation 1. So this is my equation 1. Okay, so because I know here Ft, that is the force tractive effort, I know, because the tractive effort I'll be converting into tons now. But also we know that the coefficient of adhesion, by the definition of coefficient of adhesion, we got to know that. So what is actually the definition? It will be defined as the ratio of tractive effort to slip the wheels to adhesive weight, correct? So if we take the ratio of tractive effort to slip the wheels, because when the wheel slips, then only the train movement will be happening. Okay, so hence the coefficient of adhesion between the wheels of the train and the track will be defined as the tractive effort to slip the wheels divided by adhesive weight. Okay, so this will be taken as coefficient of adhesion. So here I know the tractive effort term here. So what I can write, the tractive effort to slip the wheels, so I can write it as coefficient of adhesion, that is mu into adhesive weight. So before that adhesive weight also we have to know what is actually the adhesive weight. It is the total weight to be carried on the driving wheels, correct? So whatever the weight which is being carried by the driving wheels, so that we call it as the adhesive weight. So hence I could write as the maximum value of tractive effort that can be possible with WL adhesive weight of the locomotive. Hence, I could also write the tractive effort as mu into WL, correct? So here by the definition of coefficient of adhesion, we can define as it is the ratio of tractive effort to slips the wheel divided by adhesive weight. So adhesive weight means what? It is actually the weight of the locomotive. Hence we could write in this way. Hence the tractive effort can also be written as 0.2 into WL. Let this be equation 2. Now let us equate these expressions 1 and 2. So when we equate this expression 1 and 2, then I could write as 0.2 WL will be equals to 0.055227 into 400 plus WL. So then what will be the WL here? So the WL will be equals to upon rearranging, we will get the answer 152.5892 tons. So why I have written like this? Because first of all, I have to know what is the weight of the locomotive, because and in the problem also they have told us to calculate the weight of locomotive. Hence, to calculate the weight of locomotive, here the dead weight of the overall system as we don't know. Hence, I'm rewriting as W itself. So we have two expressions for tractive effort, one with respect to acceleration and gradient, and one with respect to the coefficient of adhesion. Hence, I'll be taking these two equations. So when I take these two equations, then when I equate these two terms, then I can easily calculate the WL. Hence, the weight of the locomotive will be equals to 152.5892 tons. So this is actually the weight of the locomotive. Hence, we have solved the first case of this problem. Next, we have to calculate the number of axles also. So how do I write? The number of axles required will be equals to the weight of the locomotive divided by allowable load, because only one axle cannot withstand the total weight of the system. So we have to provide many axles to balance the weight of the system. Hence the overall load will be shared among the wheels or the axles. Hence, we have to write in this way, that is the weight of the locomotive divided by allowable load. So what is the weight of the locomotive, which is nothing but 152.5892 ton divided by allowable load. They have only specified in the problem, which is nothing but 22 tons. Hence, we will get the answer 6.93, which is nearly equals to the 7. So therefore, how many axles are required here? Here 7 axles are required to carry this much of weight of the locomotive as well as weight of the train. So this is how we are going to solve the problem. So next, let us move on to the second problem. An electric locomotive is required to haul a train of 12 coaches, each weighing 30 tons on mainline service, requiring an initial acceleration of 0.8 km per hour per second, up a gradient of 1 in 100, estimate adhesive weight, and hence the number of axles locomotive must have if permissible axle loading is 20 tons per axle, assuming rotational inertia to be 4% for coaches and 15% for locomotive. Maximum coefficient of adhesion is 0.2 and tractive resistance 5 kg per ton. So this is the problem they have given. So here we have an electric locomotive which is hauling a train of 12 coaches. That means what? There are 12 coaches of train is there, and the locomotive should pull those coaches which are weighing 30 tons, and initial acceleration will be 0.8 kilometer per hour per second, and the gradient it is driving, which is 1 in 100. So we have to calculate what is the adhesive weight of the overall system, and we also have to calculate how much number of driving axles are required for the locomotive, and the permissible limit for those locomotives is 20 tons per axle, and the rotational inertia and the coefficient of adhesion also they have given. So let us move on to the problem. First, let us list out the data, that is weight of the train, that is actually only the dead weight of the train I am talking. So that is W is equals to 12 into 30, correct? So because one coach is weighing 30 means 12 coaches total overall weight will be 12 into 30, which is nothing but 360 tons, and alpha is equals to 0.8 kilometer per hour per second, and gradient is equals to 1% and mu is equals to 0.2. So 4% inertia they have given. So therefore, the effective weight or the accelerating weight, how do we write this? So therefore, WE is equals to W plus 0.4 W, which is nothing but 1.4 W. 1.4 W, sorry, it is not 1.4, it is actually 1.04, correct? Because 4% means that is 1. W plus 0.04. So therefore, 1 plus 0.04 means what? It is 1.04. So sorry, I have mistaken over here. So therefore, it is 1.04 into 360, which is nothing but 374.4 tons. Next, we have the adhesive weight of locomotive. So what is actually the adhesive weight of locomotive? That is nothing but WL. So what is I'm talking about the adhesive weight? It is actually the total weight which is being carried by the driving wheel. So hence we could write it as WL. And the accelerating weight of the locomotive, how do I write? It is nothing but WL plus 0.15 W, because for the locomotive also they have given the rotational inertia which is 15%. Hence the accelerating weight will not be equal to the adhesive weight of the system. So which is nothing but WL plus 0.15 W. Hence it will be equals to 1.15 WL. So now this will be the correct accelerating weight of the locomotive as well as the train. So next, they have given the resistance in kg per ton, but we need to convert it into Newton per ton to substitute in the formula. Hence, let us multiply by 9.81 to convert it into Newton per ton, because 1 kg force is nothing but 9.81 81 Newton. Hence, 1 kg. So to convert into Newton, we have to multiply by 9.81, and the coefficient of adhesion mu is equals to 0.2. So next, tractive effort, we have the same formula, that is Ft is equals to 277.8 WE plus 1.15 W, because it is the total weight of the train as well as the locomotive. So this weight I'm going to consider, that is the accelerating weight of train, accelerating weight of locomotive, which is nothing but WE plus 1.15 WL. And again we have the same formula. So let us substitute the value over here. So remember, in this formula, we have to substitute only the accelerating weight. So we should not substitute any we should not substitute any dead weight over here. Hence, it will be equals to this value. And because we know that the formula, correct, which is nothing but 277.8 WE alpha plus 98.1 G plus R into W, correct? So whereas W is nothing but only dead weight. So that is, dead weight means here it is the dead weight of train plus dead weight of locomotive, which is nothing but the total dead weight. So hence I have written only W plus WL over here. So here we need, that is in the acceleration term, we have to substitute the accelerating weight, which is nothing but the effective weight. Hence we have to substitute here the accelerating weight over here, that is WE plus WL plus 1.15, that is WE plus 1.15 WL. So remember this one, that is here we need to substitute accelerating weight, and here it is only the dead weight. Okay, so hence we will get this value. Let us rearrange this, and let us convert this Newton to tons. Okay, because if you want to equate the two equations with respect to the tractive force, they should be in a same unit. With respect to the coefficient of adhesion, it will be again in tons. Hence here also we need to convert it into tons. So how do I convert into tons? That is by dividing the answer by 1000 into 9.81. Hence, we will get 13.882 plus 0.041 WL ton. So this is the tractive effort. Let this be equation 1. So next we know that that is the tractive effort to slip the wheels, which is nothing but Ft is equals to coefficient of adhesion into adhesive weight, which is nothing but again the WL. So that is 0.2 WL. So we have two equations. Let us equate these two equations 1 and 2. So when I equate these expressions 1 and 2, then WL will be equals to 87.3081 ton. In this way, we are going to calculate what is the weight of the locomotive. Next, we have to calculate the number of axles also. So number of driving axles is nothing but what? Which is nothing but weight of the locomotive divided by the adhesive weight. So hence, which is nothing but 87.3081, and it is not the adhesive weight, it is the weight of the locomotive divided by permissible weight on the axles, correct? So therefore, it is nothing but 20, which is specified in the problem itself. Hence, we will get 4.3654, which is nearly equals to 5. Hence, how many axles are required? We require 5 axles. Okay, so hence we require 5 axles. So this is how we have solved the problem. So next, let us move on to the third problem. A locomotive of 100 tons can just accelerate a train of 400 tons with an acceleration of 1.5 km per hour per second up a gradient of 1 in 100. Assume an adhesive weight of locomotive 70% of total dead weight. The tractive resistance is 40 Newton per ton and the rotational inertia increases dead weight by 10%. If above locomotive is aided by another locomotive of 150 tons with 80% adhesive weight, determine additional trailing weight that can be hauled up same gradient under same conditions. Second one, maximum gradient, trailing haul load remaining unchanged. Third one, acceleration if both gradient or haul load remain unchanged. So please understand the problem here. So here we have one locomotive which is weighing 100 tons and which is accelerating a train of 400 tons with an acceleration of 1.5 kilometer per second. So that data they have given. That means we have one locomotive and we have one train. So therefore locomotive is drawing the train which is weighing 400 ton, and again the locomotive weight is 100 ton. So here that and all you can notice here, that is acceleration and gradient and all you can write. So coming to this this part, that is we have to calculate, so you can see here, that is if above locomotive is aided by another locomotive of 150 tons with 80% adhesive weight. Okay, so here what we are going to discuss here is, so here first case, what in the first case we have only the one locomotive and the one train which is 400-ton weighing and locomotive weight is 100-ton. In the second case, you can observe if the locomotive what we are having 100-ton, it is again aided or it is added by another locomotive which is weighing 150-ton. So that means what? Before we had only one locomotive and one train. Now we are going to add another locomotive to the same system. Hence, now we have two locomotive and one train. So if we do so, then we have to calculate what is the additional trailing weight that can be hauled by same gradient under same condition. So we have all the same condition, then what would be the additional trailing weight that can be hauled up? That means if I add the another locomotive, then again how much weight I can put on the locomotive. That is, now it is weighing only 400, it is pulling only 400 ton. If I add the another locomotive, then what would be the other weight I can add to the system. So that we need to calculate under same gradient and same condition. Then second one, the maximum gradient trailing hauled load remaining unchanged. That is, so here we have calculated in the first case, we will be calculating what will be the excess load if I add another locomotive, so that we are going to calculate. For the same load condition, we have to calculate what would be the maximum gradient it can cross, so that we need to calculate. And in the third condition, for the same gradient and for the same load, we need to calculate what would be the acceleration required to haul the load. Okay, so this is the problem. So cleanly, like first, please understand the problem, then only you can easily solve the problem. Okay, so hope you have understood the problem. Next, first list out the data. So that is the acceleration for the previous condition is 1.5 kilometer per hour per second, and gradient is 1%, and the resistance is 40 Newton per ton. So what is the dead weight of train and first locomotive? So the dead weight of train and first locomotive is what? It is 100 plus 400, which is nothing but 500 tons. So this is the total dead weight of the system. That is for first condition I am talking about. So next, this is the dead weight. Then what would be the accelerating weight or the effective weight? So which is nothing but what? So here they have given that assume an adhesive weight of locomotive is 70% of the total dead weight. So they have specified over here, and the rotational inertia is also they have given. Hence the effective weight what I am talking about. So the effective weight is nothing but what? Which is nothing but WE is equals to what? Again 1.1 times W. So which is nothing but 1.1 into 500, which is nothing but 550 tons. So now this is my effective weight. So they have given that adhesive weight of locomotive is 70% of the total dead weight. That is nothing but what? WL, what I am talking about. So this W, that is the adhesive weight, is nothing but what? Which is 70% of the total dead weight. Hence, the first we will calculate the total tractive effort. So the tractive effort required, again we are going to use the same same formula, and let us substitute the value, which is nothing but 298,235 Newton. So let us convert Newton into ton, that is by dividing by 9.81 into 1000, which is nothing but 30.4011 ton. Let this be equation 1. Again, they have specified they have given the mu value, that is coefficient of adhesion. Hence, I could write it as the maximum tractive effort for front locomotive, which is nothing but what? Ft is equals to mu into WL into adhesive weight divided by dead weight, because here we are talking about only the front locomotive or the first locomotive. Hence, this is the formula. Formula is not only the coefficient of adhesion into WL, but it is also the adhesive weight divided by dead weight. Okay, so hence we have to write in this way, because we have to write in this way. So let us substitute the value, and again here mu is unknown, that is coefficient of addition is unknown, and we have to calculate. So let us equate these two equations. Hence the coefficient of addition is 0.434. So this is the coefficient of addition. So next, what is the adhesive weight of first locomotive here? Because they have told you that that the adhesive weight is nothing but what? It is 70% of the it is 70% of the dead weight of the locomotive, correct? So in the problem they have given you that this is the thing they have mentioned, that assume an adhesive weight of locomotive is 70% of the total dead weight. So what is the dead weight of the locomotive, which is nothing but 100 ton. So therefore auxiliary adhesive weight is 70% of that, hence it is 100 into zero point 0.7, which is nothing but 70 tons. Next, what would be the adhesive weight of second locomotive? The adhesive weight of the second locomotive. So that data also they have given. That is which is 80% of the that is the another locomotive of 150 tons with 80% adhesive weight. Hence, how could I write this? That is the dead weight of the another locomotive is what, which is nothing but 150 tons, so which is 80%, that is adhesive weight is again 80% of the dead weight of the second locomotive, hence it is 150 into 0.8, which is nothing but 120 tons. So next, what will be the total adhesive weight of both locomotive, which is nothing but 70 plus 120, which is nothing but 190 ton. So next, let us move on to the data what we have to calculate. So first one, they have told you that what would be the additional trailing weight that can be hauled up the same gradient under the same condition. So now I am representing this as W1 ton. So this trailing weight we need to calculate, right? So let trailing weight that can be hauled up same gradient and at same condition will be W1 ton, because this is the again we are going to load the another weight, like another train we are going to like if I add the second locomotive, then I have to calculate what would be the additional weight I can add to the system. So hence this is I am going to represent as W1 ton. Now what would be the total dead weight now? So my total dead weight will be 100 plus 150 plus W1, because 100 is nothing but what? It is the weight of the first locomotive, dead weight of first locomotive. 150 is nothing but weight of the dead weight of the second locomotive, and W1 is what? It is the dead weight of the it is the dead weight of the system, correct? This is what I have to calculate, right? Hence it is W1 ton. Now the total dead weight will be how much? Because here I should not take only the 400 ton, because 400 ton was the weight which was carrying by only the first locomotive. So if I add the second locomotive, then what would be the total dead weight, total weight of the train by the both the locomotive, means that I am representing as only W1 ton. So now the tractive effort required is nothing but what? So the tractive effort again it is nothing but Ft dash is equals to 277.8 We alpha plus 98.1 W dash G plus W dash R. Okay, so again let me take W dash common. So hence hence here I could write as We by W dash. Hence the ratio will be again, because the 10% inertia, because they have told you that same condition we have to use, hence the rotational inertia will be again 10%, hence it is 1.1. Okay, so this ratio We by W will be 1.1. Again I'm substituting all the data as it is. Let this be equation 3 now. Okay, so so this is my equation 3, and let us convert this Newton to ton, that is by dividing the answer by 9.81 into 1000, which will become 0.0608 W dash ton. So next, what would be the total tractive effort can be developed? So the total tractive effort can be developed, again it is nothing but mu into adhesive weight of both the locomotive. So what is mu here? We have find out here it is 0.434, because it is of same condition. And what would be the total adhesive weight, which is nothing but what? 190 ton. So substitute here. So hence we will get the value. So let this be equation 4. Now let me equate equation 3 and 4. So when I equate 3 and 4, then what would be the W dash, which is nothing but 1356 ton. So please understand the problem. So what is this W dash? It is the total dead weight. In the first case, they have told you that with the the one locomotive, it will be drawing 400-ton train. So that would be the maximum weight which was drawing by only one locomotive. So now I am going to add another locomotive which is weighing 150 ton. So now I have two locomotive. Then in this problem, or in this first case, what I have calculated what would be the total dead weight which will be drawing by the two locomotive. So what will be the total dead weight then? Here it will be 1356 ton. With 100-ton locomotive, it was drawing 400 ton. When I add two locomotive, then what would be the total dead weight it can draw? It can draw 1356 ton. So this is how I have calculated what would be the additional trailing weight that can be drawn by the two locomotive. So first case I have calculated, that is the additional trailing weight that can be hauled up the same gradient under the same condition. So this is my total trailing weight, or the total weight of the system with the two locomotive. So in the second case, what should I calculate? It is the maximum gradient trailing hauled load remaining unchanged. That is, we have to calculate the maximum gradient with the same trailing haul load, that is with the same W dash, which is nothing but 1356 ton. And we have to calculate the maximum gradient. So let us go on to the next case, that is in the second case. The trailing weight is nothing but what? Which is nothing but W1 is equals to W dash minus 100 minus 150, which is nothing but 1356 minus 250, which is nothing but 1106 ton. So this is the total trailing weight. Okay, so here I have calculated, please note that W dash is nothing but what? It is the total dead weight. So what would be the W1? 100 plus, so you can see here the total dead weight, that is weight of locomotive plus weight of train. So weight of locomotive was 100 plus 150. So what would be the weight of the train, which is nothing but W1? What would be the W1, which is nothing but 1356 minus 250, which is nothing but what? That answer. So what is W1? Please note that it is the trailing weight of the train. Okay, so like what would be the trailing weight, which is nothing but 1106 ton. So this is the first case we have calculated. So first case we have calculated what would be the weight of the train, which is nothing but 1106 ton. So next we have to calculate what would be the gradient. So now let us write in this way, that is W dash is equals to what, which is nothing but 400 plus 100 plus 150, correct, which is nothing but 650 ton, because this is the weight of the train, because it is the weight of the locomotive, that is 100 plus 150 will be my weight of the locomotive. What would be the 400? So it was the weight of the train, correct? The previous train they have given, which is nothing but 650 tons. Okay, so please remember that trailing weight is different, and trailing load or trailing weight is different, and the haul load is different. Okay, the trailing weight is nothing but this one, that is 1106 ton. The total haul load is nothing but what? It is overall system, that is weight of locomotive plus weight of the train. So which is nothing but 650 tons. So hence we have taken only the haul load, that is 400. So here we have not taken trailing weight, because in the second problem they have second case they have specified that what would be the maximum gradient if the trailing haul load remaining unchanged, that is 400 tons, that is the previous train weight what it was, that only we have to take. So please remember this, haul load is different and trailing weight is different. So now what would be my WT dash, which is nothing but again the same formula we are going to use. Instead of that is the dead weight will be now 400 plus 100 plus 150. So now again let it be in Newton. It was in Newton. Next we need to convert it into ton. Let us divide by 9.81 into 1000 to convert it into ton. Let this be equation 5, and they have told for the same condition. So now let us equate again the equation 5 and equation 4. So when I equate equation 4 and 5, what would be the answer? Which is nothing but So which is nothing but what? Let us equate these two equation. Here gradient I don't know, because for the same acceleration and for the same resistance I need to calculate the maximum gradient, and G is retained as it is. So hence let us equate equation 4 and 5. So when I equate equation 4 and 5, then what would be my gradient, which is nothing but 7.06059%. So this would be my the gradient when during the same Hall load and the same other condition. Okay, so hence we have calculated the second case. So in the third case, what we need to calculate, the acceleration we want to calculate if both gradient and Hall load remain unchanged. Okay, that means what? The gradient is same. That was in the first case what we have discussed. So it's the same gradient, and the Hall load. Hall load means what? It is only the weight of the train when it was drawing by the one locomotive. That is nothing but 400 tons. So therefore, the tractive effort required, again it will be same thing, that is W double dash we have written over here. Hence, which is nothing but 650 tons. So same Hall load we are going to take over here. That is nothing but double dash only. That is nothing but 650, converting Newton into ton. Next, let this be equation 6. Now let us again equate equation 4 and 6. Hence, we will get the acceleration, that is the new acceleration with the other locomotive, which is nothing but 3.62 kilometer per hour per second. Hence, we have calculated all three cases. So in the first case, we have calculated the additional trailing weight we have calculated for the same gradient and under the same condition. So the trailing weight what we have taken, that is trailing weight means what? It is the weight drawn by the two locomotives. Okay, so that we have taken as trailing weight. Okay, so in the second case, we have calculated maximum gradient with the same Hall load. Hall load means what? It is only the weight of the train which was carrying by one locomotive, that is 400 tons. So please remember this. Trailing weight means what? It is the what would be the overall weight which can be drawn by the two locomotive. Hall load means what? It is only the weight which is drawing by one locomotive earlier. So that we have taken over here, that is only the weight of the train plus weight of both the locomotive. So this is how we have calculated the gradient. And in the third case also the same Hall load we have used, and the gradient also you can see here, we have used the same thing, that is 1%, which was in the first problem they have discussed. So that is only the thing we have taken. So here you can see here 7.6059% gradient we have got. So this we have not used over here. We have used only the gradient for the one locomotive. So like that we have calculated all three cases. So next we will move on to the last problem. A train with a locomotive having 4 motors has a total mass of 250 ton. Starting from rest, train attains a speed of 40 km per hour in 20 seconds on a 1% up gradient, and the gear ratio is 3. The gear efficiency is 95%, and the wheel diameter is 95 centimeter. And the train resistance is 40 Newton per ton, and the rotational inertia is 10%. Find the torque developed by each of motors, and minimum weight of locomotive given adhesive coefficient is 0.25. So what they have given over here? So they have given the train with a locomotive having 4 motor. So the locomotive section is having 4 motor, and the mass of each motor is 250 ton. Sorry, the total mass of 4 motor is 250 ton. And the acceleration is 40 kilometer per hour in 20 seconds. And the gradient they have given, and the gear ratio gamma they have given, gear efficiency eta they have given, wheel diameter also they have given. Here we need to calculate the torque developed by each motor and minimum weight of locomotive. So how do we solve this? So in the derivation, that is on the mechanism of train movement, so there we have derived the formula. So let us use the same formula over here. So let us list out the data, and equation equivalent accelerating weight of the train, that is W is equals to 1.1 W, which is nothing but 275 ton. And the time taken to accelerate train, that is T1 is equals to 20 seconds. And I could calculate the acceleration. Acceleration is nothing but what? Alpha is equals to maximum speed, that is Vm divided by T1, correct? So here you can see here 40 kilometer per hour. So this is only the speed. This is not acceleration. What is the unit of acceleration? It is kilometer per hour per second. But they have mentioned here only kilometer per hour, hence it is only the speed. So hence speed by time is nothing but acceleration. So that is nothing but Vm by T1, which is nothing but 2 kilometer per hour per second. Next, what would be the total tractive effort? Again, let us use the same formula and substitute all the data. We will get 1,87,315 Newton. Again, to convert it into ton, let us divide by 9.81 into 1000. Hence, we will get the value in terms of tons. Next, what would be the total torque developed? So, in the mechanism of train movement, we have solved this. We have derived this. That is total tractive effort. T we have to calculate, which is nothing but Ft into D divided by eta into 2 gamma. So Ft we know diameter. Here D is nothing but diameter, not distance. So the diameter of the wheel we have, and the transmitting efficiency we have, and the gauge ratio is also we have. Let us substitute all the value, which is nothing but 31,000 to 19.16667 Newton meter. And this is what it is, the total torque developed, correct? So it is the total torque developed, but we have to calculate what is the torque developed by each motor, because we have to find out what is the torque developed by each motor. So how many motors are there? We have 4 motors. So what would be the torque developed by each motor, which is nothing but total torque developed by number of motors. Hence it is nothing but 7804.7916 Newton meter. So hence we have calculated the first case, that is torque developed by each motor. So next we have to calculate what is the minimum weight of the locomotive. So how do we calculate that minimum weight of the locomotive? Because minimum weight of the locomotive is nothing but what? Which is nothing but the adhesive weight, correct? So we have the formula for the coefficient of adhesion, because coefficient of adhesion is defined as what? It is the total tractive effort to slip the wheels divided by adhesive weight. So hence what would be the adhesive weight or the weight of the locomotive, which is nothing but WL will be equals to what? It is nothing but FT by mu. Hence we have taken in this way, which is nothing but 76.37716 ton. So next, assuming an adhesive weight of the locomotive to be 75% of its dead weight, we have dead weight of the locomotive, correct? So here we also have to calculate the minimum weight of the locomotive, that is the dead weight of the locomotive. Hence we are assuming that adhesive weight of locomotive is 75% of its dead weight. Hence I could write as WL by 0.75, which is nothing but 76.37716 divided by 0.75, which is nothing but 102 ton, or 1.8362 ton. So this is actually the minimum weight of the locomotive. So please be clear with the definitions, that is adhesive weight, what is the dead weight, what is accelerating weight. So the definitions we have to be clear, then only we can actually calculate the problem. Okay, so this is how we have calculated the dead weight and also the torque developed by each motor. Hence it completes the designing of the some of the design problems related to the train movement. Thanks for watching the video.